So, my name is Hartmut Müller, and it is a great pleasure for me to participate in this conference. Thank you for invitation. My contribution is about superluminality and scaling and their cosmological significance. It's moving as well.
Yes.
At least with the speed of light. I remember well that beautiful day in 1997 when my teenage son was asking me, "Daddy, why is the speed of light is so slow?" In fact, 300,000 kilometers per second is not very high regarding even the solar system. In interstellar and intergalactic scales, it becomes obvious how disappointingly slow it really is. 1 year later, regarding reading on the pioneering research of Günther Nimz, my heart started to beat faster. Already in 1992, Enders and Nimz demonstrated that photonic tunneling proceeds at superluminal signal velocities. The signal velocity is the velocity of the transmitted information. Later, they carried out superluminal amplitude modulated and frequency modulated microwave experiments using different photonic barriers. Wolfgang Amadeus Mozart would be excited to know that his 40th symphony was tunneled without any significant distortion at the speed of 1,410,000 kilometers per second. That is 4.7 times higher than 300,000 kilometers per second. In 2002, Longier and colleagues demonstrated superluminal tunneling of infrared pulses. In the propagation of electric pulses along coaxial lines having spatially periodic impedances were observed velocities of about 800,000 kilometers per second. Nevertheless, superluminal tunneling is still under discussion. However, while Nimz argues with facts and measurements for superluminal signal transmission, his opponents counter with poorly theoretical approaches. One of the main counter-arguments is the alleged violation of causality. Causality requires the existence of a maximum speed of physical interaction, but could it be that 300,000 kilometers per second is already high enough? This is very unlikely if we consider the stability of galaxies and the unity of the universe up to scales of billions light years. Tunneling experiments show that the conditions required for superluminal signal transmission are not exotic. Therefore, it is possible to imagine that those conditions can emerge also in nature or in deep space, and astrophysical observations already suggest this possibility. Already in 1999, superluminal motion was observed in the jet of the galaxy M87. many of the jets are evidently not close to our line of sight, as you can see in this photo of M87. Therefore, their superluminal behavior cannot be dismissed easily as an illusion. Exceeding 300,000 kilometers per second has nothing to do with time travel, grandfather paradox, or any other violation of causality. This would be relevant in the case of an infinitely high velocity. Furthermore, 300,000 kilometers per second does not follow from any established theory, and consequently, none of those theories had to be changed if the speed of light would be even 55 times higher than 300,000 kilometers per second. Within the special relativity theory, the speed of light is only postulated, not derived, to be stable and maximum. Up to now, there have not been sufficiently convincing explanations why the speed of light should be stable and why it should have the value that it has. What exactly makes possible to exceed 300,000 kilometers per second? The point is that the tunneling time does not depend on the length of the barrier. Thomas Hartmann theoretically described this in 1962. The tunneling time equals approximately the reciprocal frequency of the carrier wave, as we can see in this table, independently on the length and the type of the barrier. Exactly this circumstance makes possible to exceed 300,000 kilometers per second. In this article, Günther Nimz annotates, we are used to expect virtual particles in microscopic interaction. In fact, the stability of the speed of light and its value, 300,000 kilometers per second, must have a subatomic origin. In the last century, advanced theories were developed which model subatomic processes. However, modern particle physics remains a supermarket offering too many articles. The current population of the particles, though, includes 137 baryons and baryon resonances, as well as 240 mesons and meson resonances. Theoretically, composed of 6 flavors of quark, up, down, strange, charm, bottom and top. Furthermore, the leptons, electron, muon, tau, and the corresponding neutrinos, but also photons, gluons, vector and scalar bosons that theoretically intermediate the interaction between all other particles. Graviton, axion, dilation, inflation, and chameleon are expected. Although the population of the particles, though, is continuously increasing, the sequence of the corresponding energy levels we see in this table and masses remains to be a mystery. In the standard model, particle masses appear as to be accidental. A rough shortcoming of the Higgs model of particle mass generation is that the origin of the Higgs mass itself is not elaborated, and this leads to a vicious circle. The absolute majority of the known particles is unstable, having lifetimes in the range of nanoseconds, picoseconds, or less. For instance, the lifetime of the Higgs boson is less than a yoctosecond. That is a millionth of a billionth of a billionth of a second. It is 0.23 zeros of a second. It is very hard to measure. On this background, the stability of the proton and the electron seems to be a miracle. The lifespans of the proton and the electron surpass anything that is measurable, exceeding 10 to the power of 30 years, not seconds. That is more than 1,000 billion of billions years. And I was not stuttering. Naturally, no scientist ever witnessed the decay of a proton or an electron. Well, but what is the secret of their eternal stability? Elementary particles are quantum oscillators. Their energy and mass depend on the oscillation frequency. In the case of an integer mass ratio, also the frequency ratio would be a whole number, and the oscillations of the proton would pump up the electron. This animation did show the case of the so-called parametric resonance. A permanent proton-electron resonance would ultimately stabilize any atom. The formation of molecules would be impossible. Biological life would be impossible. Fortunately, fundamental particles avoid integer frequency ratios. Ratios of integers, mathematicians call rational numbers. As we already clarified, source frequencies, or frequency ratios, provoke destabilizing resonance interaction and therefore must be avoided. Very different are irrational numbers. They are not ratios of whole numbers, and consequently they should not cause destabilizing resonance interaction, and therefore, for example, the square root of 2 is irrational. However, irrational numbers like the square root of 2 or other roots do not compellingly prevent resonance, because they transform into whole numbers by multiplication. The square root of 2 multiplied by itself equals 2. Consequently, already if two frequency ratios coincide with square roots, they can provoke destabilizing resonance. Fortunately, there is a type of irrational numbers called transcendental, which are not roots. They do not transform into rational or whole numbers by multiplication, and consequently they definitely do not provide resonance interaction. Probably the best known transcendental number is pi, but there are infinitely many transcendental numbers. Among them, only Euler's number, E, fulfills another very important criterion. Euler's number is the basis of the natural exponential function, the only function that is a derivative of itself. The derivative, as you know, is a rate of change. Why is this so important? Actually, frequencies of real processes are not constant. Therefore, to reach lasting stability, a real system must avoid resonance not only regarding the frequencies, but also regarding their rates of change. Only Euler's number can guarantee this. In this way, Euler's number provides a solution for lasting stability in real systems of any degree of complexity. Probably Euler's number is a main stabilizer in the universe. Euler's number and its roots are attractors of transcendental numbers that inhibit destabilizing resonance. Euler's number determines scales of stability and in this way makes possible the formation of fundamental particles. Actually, the proton-to-electron mass energy and frequency ratio approximates the 7th power of Euler's number and its square root, and it is a very good approximation. By the way, the Sun to Jupiter mass ratio approximates the 7th power of Euler's number, and this is also a very good approximation. This is the proton-to-electron mass ratio. The 12th power of Euler's number creates the vector bosons. The 12th power of Euler's number and its square root creates the Higgs boson. The absolute majority of hadrons approximate integer powers and roots of Euler's number. In the first column we see the logarithm, means the power of Euler's number. In the bottom you see 7.5. It is creating the proton and the neutron. And then the 8th power, the up-down hadrons, the 8th power and the square root of Euler's number, the strange hadrons, the 9th power of Euler's number, the charm hadrons, and then the bottom hadrons and the top hadrons. All of them, if we look at a histogram of the distribution of their mass ratios relatively to the proton or the electron, they approximate the integer powers of Euler's number and its square root. In addition, their stability level correlates with the approximation level of Euler's number. Finally, the 44th power of Euler's number creates a Planck particle. This makes very likely that the Planck particle exists and that it is stable. The Planck mass directly originates from the fundamental constants. The Planck constant, the speed of light in a vacuum without any barrier, and the gravitational constant. If now we consider the Planck to proton mass ratio, that is exactly Euler's number to the power of 44, then we can write down this equation. And on the right side of this equation, the right side is dimensionless. Therefore, here we have a velocity. Cp is the velocity of two protons at the distance of the Planck length in free fall after Planck time. And now we can derive the 88th power of Euler's number that defines the velocity of 300,000 kilometers per second. The identification of this speed with C88 is a key step. C88 is the velocity of a stable process that we call propagation of light in a vacuum, naturally without tunneling barriers. Considering the stabilizing function of Euler's number, now we can derive not only the velocity of 300,000 kilometers per second from other fundamental physical constants, but also the velocities of other stable subluminal and superluminal velocities and processes, which correspond to rational powers of Euler's number. This table shows some of these velocities. All of them are superluminal. And all of them already were observed in astrophysical processes. For example, in active galactic nuclei, quasars and gamma-ray blazars. I have analyzed all these velocities, and all of them approximates the integer powers and roots of Euler's number. There are really many in these publications, and everybody can analyze. Superluminality is of cosmological significance because only exceeding the speed of light, gravity can form solar systems and galaxies. By the way, in astronomic calculations, gravitation is traditionally considered as being instantaneous. Gravitation does not show aberration. First, Laplace demonstrated that gravitation does not act with the speed of light. The stability of the solar system, in detail the stability of the Earth's orbit, requires that gravity interaction proceeds with a speed that it is at least 7 million times higher than 300,000 kilometers per second. In 2013, the NASA astronomer Thomas van Flandern confirmed a lower limit of 20 billion times. In the last century, advanced models were developed which explain basic features of the solar system. However, these models do not explain why Jupiter's orbital period is 11.86 years, but not around 10 years or around 13 years. why Saturn's orbital period is 29.46 years, or why Pluto's orbital period is 247.94 years. In all models, their current orbital periods appear as to be accidental. The problem is that the Kepler laws of planetary motions, the Newton law of gravitation, and even the Einstein field equations allow for an infinite diversity of orbits. In the past, this circumstance counted as a sign of abundance. Today, after the Kepler Space Telescope discovered thousands of exoplanets, it becomes obvious that this uncertainty simply indicates a lack of knowledge. Planets in the extrasolar systems, TRAPPIST-1, Kepler-20, and many others, have nearly the same orbital periods as some moons of Jupiter, Saturn, Uranus, and Neptune. TRAPPIST-1 is 40 light years away from the solar system. Kepler-20 over 900 light years, and Kepler-11 over 2000 light years. Why they prefer similar orbital periods if there are infinite possibilities? The secret is that the ratios of the orbital periods of the planets and large planetoids approximates integer powers of Euler's number and its square root. The transcendence of Euler's number avoids destabilizing orbital resonance between the large planets. The scale below is logarithmic. The graphic shows the planets and large planetoids in the logarithmic sequence of their orbital periods. Integer powers and roots of Euler's number are attractors of transcendental numbers. They form islands of stability where planets can form and move in stable orbits. These attractors cause the effect we call gravity. Mass accumulation is only a consequence. Multiplying the orbital period of Jupiter by Euler's number 3 times, we can approximate Pluto's orbital period. Very precisely, you can prove it. Dividing the orbital period of Pluto by Euler's number 6 times, we can approximate the orbital period of Venus. This procedure mathematicians call scaling. Since 40 years, I am developing an approach that I call physics of numbers, especially the physics of transcendental numbers. Numbers are scalars, and scaling is a key procedure in the universe of numbers. Numbers are omnipresent and in this sense non-local. Therefore, the physics of numbers acts instantaneously. Quantum physical entanglement and gravitation are some of the most expressive examples. Physics of numbers is relational and considers conventional models of intermediating fields and their charges and forces as outdated. Euler's number is a universal solution of lasting stability, and this solution is given a priori, and it is not necessary to search it through competition and selection. More information on this topic and many examples, over 200 examples, you can find in my book, Global Scaling, the Fundamentals of Interscalar Cosmology. You can free download on the Interscalar homepage. Thank you for attention.